This is our fourth example problem of a composite product of inertia problem where we use the parallel axis theorem. This particular shape is actually located pretty much at the origin. And so we're just going to use, for the most part, the at origin forms of the equations for IXY. So again, this is our example problem 4. We've got a shape that looks like this. And so it's mostly centered at the origin of the XY axis. There's a right triangle here that touches the origin. There's a quarter circle here that touches the origin. There's a rectangle here, I'm sorry, a square here that touches the origin, and a square here that touches the origin. And so we want to find IXY for this shape. I did IX and IY, but coming down to IXY. And so for the right triangle in this corner here with its right angle at that corner, that's going to have a negative, this guy here is going to have a negative sign, and it's going to be 0.04167 b squared h squared. So negative 0.04167 b squared h squared, nestled in that corner. For my quarter circle, he's nestled into this corner, and our formula for him is this guy. So he's a positive 1/8 r to the 4th. One over 8 r to the 4th. Finally, for the rectangle, I could have, for this lower piece, I could have used two different corner terms for these squares, but I chose to, and they would have canceled one another out. They would have been 0. So one of these would have been, let's check our signs. So this guy would have been positive 1/4 b squared h squared. This guy would have been 0. Once we added them up, they would have canceled one another out. We chose to apply the product of inertia to the whole rectangle, but his I bar is 0. His area is 2 times 4. His dy is -1, but his dx is 0. And so we have a 0 for his I bar, an area, a dx is 0, and a dy is -1. So that lower rectangle, his IXY is 0. And so either way, we get that as to be 0. And so finally, the IXY for that shape is negative 0.667 plus 2. So it's 1.33 inches to the 4th. And again, I chose this because it illustrated some of the I origin equations.